In the last module, we have discussed grouping of individuals according to similarity. As you may have observed, that grouping of individuals primarily depends on the distance measures, the distances between individuals as well as distances between clusters. So, distances are a fundamental concept when we do clustering. Now, distances actually depend on the type of variable that we are looking at. The variables can be of several types. It can be numerical by nature or it can be categorical. So, different types of distance measures need to be defined for each type of variable. In the last talk, we had been looking at two types of distance measures primarily. One was the Manhattan distance and the other was the Euclidean distance. Both of these distances are again concerned with variables which are continuous by nature. But then very often variables may be of success failure type. It can be multi-category. So we need to look at how we define distances between individuals based on M characteristics, where each of these characteristics may be of different types. Recapitulating from what we did in the last module, we'll start with the city block distance. The city block distance is the distance between two vectors such that we take the differences of each element of the two vectors, take the modulus of this, and this sum it up over all the possible variables. Let's look at an example for this. Suppose we have 2 points. We start with A and we want to reach B. So we start with A and move vertically upwards first, then take a right angle turn to the right after some distance. Then again we take a left turn and go vertically upwards, and finally a right turn takes us to B. As you can see that we are taking 90 degrees turns at each point. Now this is what is referred to the city block distance. As opposed to this, we have what is referred to as the Euclidean distance. The Euclidean distance is the square of the difference between the elements summed over all the elements and then the square root of this. In terms of going from A to B, it is basically the diagonal distance from A to B. And as you can see, the Euclidean distance is far shorter than the city block distance. Now, in general, when we think in terms of distances, we first need to identify the type of variable that we are looking at. There are two types of variables. One is variables which are numerical by nature, and the second are variables which are categorical by nature. Again, numerical variables can be classified into continuous, like height, age, etc., which takes continuous values within a given interval. As opposed to this, we have the discrete variables like family sizes, which takes just integer values. But both the continuous and the discrete are in the form of numerical values. So it's easy to work with this while defining distances. On the other hand, categorical variables are variables which can be classified into a number of groups. The simplest of the categorical variables, and for certain reasons the easiest to handle, are the binary variables, which are primarily two-category variables. A very quick example of this would be if we are looking at gender, males and females. Another example would be if we are looking at the tossing of a coin, like head and tail. So there are two outcomes in this case. Very often, however, the categories may be more than 2. We call this multi-category variables. One example would be color. Color we can have blue, red, green, yellow, etc. And in this case, of course, it's not one or the other, but it can be one of several. Now, distances need to be defined separately for each of these types of variables. First of all, we'll look at the continuous variables. And for this, we look at what is referred to as a distance matrix. So let DRS be the distance between the rth and the sth individuals. So we have two individuals, R and S, and we are trying to find out the distance between these two individuals. Both these individuals have M characteristics. Now the distance between these two vectors corresponding to each of these two individuals needs to satisfy some conditions. The first of these conditions is that DRS must be greater than equal to 0 with equality if R is equal to S, which means that if you have the same person, that is DRR, then the value should be equal to 0. What does this mean again? It means that if I am defining a distance from A to B, this distance must always be positive. So we cannot have a negative number, which is very logical, of course. The second condition it must satisfy is DRS must be equal to DSR. That is, the distance from A to B is the same as the distance from B to A. The third condition, which is referred to as the triangle law, states that DRS plus DSQ should be greater than equal to DRQ, which means that sum of two of these distances in a triangle must always be greater than the third. So if I am going from A to B and then from B to C and then from C to A, then the distance between AB should be less than the distance between B to C and C to A. So if I am going directly from A to B, I will be going by a shorter route than if I am going from A to C and then to B. So most general measures of numerical variables would be what is referred to as the Minkowski matrix. The Minkowski metric or the LP norm gives us a distance measure which is xrj minus xsj modulus of this to the power of p, again summed over j, and then to the power of 1 by p. As you can very readily see that if p is equal to 1, we go back to the city block distance. Whereas if p is equal to 2, we have the Euclidean distance. So the city block and the Euclidean distances come out as special cases. However, visualizing something for p is greater than 2 is somewhat difficult, except for a very special case. And that special case is the Supremum norm or the infinite norm. That is, when we take p equal to infinity, what we actually is looking at is the maximum of the differences between xrj minus xsj, maximum over all possible elements. So this is generally easier to do, although we have p equal to infinity in this case. But in most cases, p greater than 2 is difficult to visualize. So generally the city block or the Euclidean distances are preferred over any other distance. Now you can also see that the distances are smaller the larger the value of p is. That is, if q is less than p, then DRSP is going to be less than equal to DRSQ. And this we have observed for the city block and the Euclidean distances. We saw that the Euclidean distance with p equal to 2 is shorter than the Manhattan distance with p equal to 1. But then one problem that arises when we look at distances is that the LP distances are affected by a change in the scale of the variables. Of course, there are exceptions like the city block and the Supremum norm distances, but all other LP distances are affected by change in scale. What is meant by a change in scale? Let's look at an example. Suppose we have 3 persons and we measure their heights in meters and also take their weights in kgs. So the first person A has height 1.68 meters, weight is 65. B has 1.75 height and 75 kg weight. C has 1.60 meters as height and 72 as weight. Now what is the distance between A, B and C? If we use the Euclidean distance, then the distance between AB turns out to be 10, between A and C turns out to be 7, and between B and C turns out to be 3. So we can see that B and C are closer to each other. On the other hand, if we now measure for the same person the height in centimeters instead of meters, so that instead of 1.68 we have 168 centimeter as his height, and similarly for B and C, and keeping the weights as they are before, we are measuring them in kgs and recalculate the distances between them using the Euclidean norm again. Okay. In that case, we find that the distance between AB turns out to be 12, between AC turns out to be 10, and BC turns out to be 15. So we now see that A and C are closer to each other. In the previous case, we had B and C closer. Now we have A and C closer to each other. So you see, we have a difference in the clustering of the groups, in this case the 3 individuals. So which of the two is correct? Okay, there are no hard and fast rule, but we should be aware that just changing the scale from meters to centimeters changes the pattern of grouping. Why does this happen? Primarily because if you look at the first group in meters, these values are very small, 1.68, 1.75, 1.60, as compared to the weight values, which are 65, 75, 72. So the weight plays a dominant role in this grouping. Whereas in the second case, the heights numerically are almost 2.5 times to 3 times the weight. So now the heights play a more dominant role than the weights, and hence they change the pattern of pairing or the distances between the different pairs. Okay. So scaling is an important aspect that we need to look at. One way of avoiding this problem is to look at what is referred to as the Mahalanobis distance. The Mahalanobis distance is given by, now we are looking at the whole vector, not the elements of the vector. So we are looking at the rth individual's observation vector xr and the sth individual's observation vector xs, which are m-dimensional. Take the difference of these two, which will again be a vector. Then we look at s. S is the standard deviation, okay, or in this case the variance calculated between the different individuals in the grouping problem. So S actually, we take the inverse of S, which acts as a norming factor in this case. So it basically scales down each of the variables, and then hence it gives a natural scaling which helps us to avoid the ambiguity that we had in the previous problem. So this is a very natural way of doing it, and it also takes into account the intravariable correlations. There are other methods, but before I come to that, let's have a look at how to calculate the Mahalanobis distance. we'll go back to the same problem. And what we need to do is, first we need to calculate the mean heights, which is 167.67, 70.67. Of course, the mean of this height and the mean weight are not directly related, but then you need to calculate the covariance matrix also, and you'll need the means for this. The covariance between height and weight is 9.83. The variance of height is 56.33 and the variance of weight is 26.33, giving us the covariance matrix. Now if we use the Mahalanobis distance, you can see that if I am looking at A and B, the first two individuals, then we have this 168 is the height of A minus the height of B, then the other element is the weight of A minus the weight of B, and then we have the S matrix, which we have the covariance matrix, which we have calculated on the basis of all the three members, and then again the transpose of the first vector, and this comes out to be 8.06. So this is basically a normed measure where we have actually scaled down the original variables. Alternative scaled measures are the Gauss measure. Now the Gauss measures uses the range as the norming factor, and it uses the range to divide the absolute difference between the elements of the rth individual and the sth individual, sum them up and then divide it by m, take the average of this. So unlike before where we are just looking at, if you look at the city block distance, then we do not use Rj, so we take Rj equal to 1. So in this case what we are doing is, we are norming each of the variables by their ranges. So the larger the range, the larger the norming factor in this case. And once we do that, we get a very scaled version of what we did for the city block distance. Alternative measures, of course, these are not so well used, but these are, you can get an idea of how to scale down variables. So instead of using Rj, what we can do is, we can use the sum of xrj and the xsj as the norming factor. This is referred to as the Bray-Curtis measure. As opposed to this, we have the Lanson-Williams measure, which is 1 by m, j equal to 1 to m, that's again the absolute difference, this time divided by the sum of the two variables. So you can see that one important aspect that we have to keep in mind is that when we look at several variables in a vector, these variables, the distance between these two vectors will depend on the scale of the variables. So if we change the scale of one variable with respect to the others, then probably the distances would become different and hence would affect the way we cluster the variables. In today's talk, we have discussed different types of distance measures. Primarily, distance measures are of two types, the numerical measures and the categorical measures. What we have been concerned with in today's lecture were the numerical measures of distances. What we will continue with in the next lecture would be the distances for categorical variables.